Okay, this is the title of my talk. It is an overview of recent developments in big Boolean equations. I might apologize for using the word big because it is not a scientific word, but I am using it because the term Boolean equations has been now used in a strange way in scientific circles. People use it to mean just the two-valued Boolean algebra, which we can simply call switching algebra. I will explain this point further as we go ahead. Next, please. Now, yes. This slide shows the topics covered in my talk. We will start with an introduction, then discuss the need for what we call a big Boolean equation solving, and then we will go quickly through some of the mathematical derivations. Of course, I'm not expecting people to follow the derivations in a very short talk, but I'll try to explain the most important aspects related to these derivations. There will be a discussion about the comparison of algebraic and map methods. Of course, as you realize now that map methods are my favorite techniques. Then we will go through an illustrative example that will explain to you much of the details, and then we will conclude the talk. Next, please. Actually, the study of Boolean equations in big Boolean algebras has been there for almost 2 centuries. We are standing on the shoulders of giants like Boole, Schroeder, Whitehead, Gortetsky, Löwenheim, Residue, and Brown. Many of these giants lived 2 centuries or 1 century ago, but only the last 2, Professor Residue and Professor Brown, are our contemporaries. Next, please. This slide, of course, the topic of big Boolean algebras has been a topic of mathematical curiosity for a while, and has gone a long way. But now it started to have many engineering applications, and particularly applications in digital logic design and in cryptography. This slide summarizes some of the topics within logic design in which big Boolean algebra is used. Sometimes it is used without recognition that it is really used. Some of the topics are the decomposition of Boolean functions, fault diagnosis in digital circuits, hazard-free synthesis of digital circuits, construction of binary codes, flip-flop excitation, and the design of sequential circuits. Next, please. There are other areas other than the 2 famous areas I mentioned in which Boolean equation solving has been applied, which include biology, grammars, chemistry, law, medicine, spectroscopy, and graph theory. Next, please. This figure is very important to give you a glimpse of what we are talking about. As I said, there is the word Boolean algebra is used as a misnomer, indicating the two-valued Boolean algebra, in which the carrier of the algebra itself contains just two elements, 0 and 1. Note that this is the minimum number of elements that we need, such that the 0 and 1 elements are distinct. In our school of thought, we are using B2 as the smallest algebra. So actually, there is an atomless algebra called B1, in which 0 and 1 are the same. Here, the figure to the right shows a hypercube lattice. This is what we call B16, which consists of 16 elements. Note that by definition, a Boolean algebra, or mathematically, a Boolean algebra is a complemented distributive lattice. And it can be otherwise defined through the property of partial ordering. If you look here, you can distinguish 16 elements, which happen to be the 16 functions built on two variables, on two switching variables. We call these elements as belonging to the free Boolean algebra of A and B. If you look at some of the points, you will see familiar notation. Like, for example, you'll find an element called A or B. The lowest element is 0 and the top element is 1. You can look at the equation below, giving you an example of partial ordering. For example, 0 is less than or equal to A bar, B bar, which in turn is less than or equal to A bar, which in turn is less than or equal to A bar, or B bar, which in turn is less than or equal to 1. The figure for B16 includes smaller algebras. For example, we can set one of the atoms, any one of the 4 atoms for this algebra, like the atom AB, we set it to 0, then we will replace the hypercube by a cube. And this cube will be the algebra B sub 8, which is the next lower algebra. Remember that we are dealing here with algebras which are finite. And it is proven that a big Boolean algebra, a finite Boolean algebra, is atomic, and it will have 2 to the power n elements. So we have B2, B4, B8, B16, and so on. We will come back to this later when we solve the equations. Next, please. We now go to the second item in our talk, which is to talk about the need for big Boolean equation solving. Next, please. Next, please. Here there is a generalized digital circuit design. This circuit was formalized by Lidley in 1959, in which we have a parent combinational circuit C that comprises two subnetworks A and B. If you see here, there are certain quantities involved here. The output of subnetwork A, Z as a function of X. Remember, all of these quantities are vector quantities, and their elements are two-valued Boolean or switching quantities. We have Z as a Z of X as a relation of output to the input of A. And for network B, we have S of Z and Y as an output for network B. The output for the overall network can be called T of X and Y. So we have three functions here. This means that we can be confronted by the problem of having two of these functions and requiring to get the third. So next, please. Okay. In the figure before, we have these, in these problems, we'll obviously need to use the big Boolean algebra because, for example, in many of the problems given, for example, if I have Z as a function of X, I can get a relation relating, or a function relating Z to X, and then try to either to express Z in terms of X or X in terms of Z. In this case, the need for the big Boolean algebra is not avoidable, and I'll have to resort to it. Next, please. An important feature of Boolean algebra is that if I have a system of equations, then this system of equations, whatever its number is, 2 equations, 3 equations, 1,000 equations, 1 million equations, whatever its number may be, can be reduced to just one equation. And this is very important. In fact, I have seen papers on cryptography in which people will have, for example, something like 1 million equations, and then they will start solving these equations separately, and then getting the general solution as the intersection of the solution sets they obtain. And instead of this, we can combine the whole system into a single equation and then solve it. The mathematics given here is related to the Lidley problem that we have before. So in the problem, as you can realize that the function S and the T in the figure that we displayed are the same. So one of them depends on certain variables and the other one depends on some other variables. Next, please. Here is how to combine such vectorial functions. We know that we need to form an equation, a single equation, H equal 1, instead of the system of equations that we have. The system of equations that we had was S sub I equal T sub I for I equal 1, 2, up to L. So we can combine them by having this. The symbol in equation 2b is the coincidence function, we can use a coincidence or equivalence function and then get the product or ANDing of all of these to form the function x. The dual situation appears below. Instead of getting an equation h equal 1, I can get an equation r equal 0 by using the dual situation. Next, please. There is a recent development due to Brown in his paper in 2011 about obtaining the resultant of suppression of variables y. For example, I have an equation r of x, y, z, in which the variables y are intermediate variables which are not accessible. They are not controlled to be inputs or observable to be outputs. And when I write a specification, they must appear in my equation. All the policy to handle this equation was to solve the equation r of x, y, z, and I solve it for z in terms of x and y, and then search among the solutions for those solutions that do not depend on y. The breakthrough that Brown achieved in 2011 is that he formulated a new function, as you can see here, which he calls the resultant of suppression, and this equation will involve only x and z. And when I solve the equation f of x and z equals 0, if I solve this equation, I get just the solutions I need. So this amounts to a big saving in efforts. In fact, in his paper, he cited examples, for example, of equations in which I can get something near 1 million solutions. And then I search among these million solutions to get just 4 solutions or something. So this is actually a big leap forward that makes the applications in digital design more accessible. Next, please. Next, please. Here we describe the equations or the method that how to get general parametric solutions. I should mention before I proceed that there are 2 main types of solutions for Boolean equations or big Boolean equations. There are general solutions, of which one type is called the parametric, which according to the name, we will get the solution in terms of parameters. And there is substantive solutions in which I get my solutions or variables subsumed in intervals. We will see examples of these later. But this example here will show you how I needed to use the big Boolean algebra. I have the function g of x and z, which, because the vector x has k elements, the vector z has n elements. So this function takes me from a domain of b2 to the power k plus n to b2. So as you see, everything is innocent. I just need the 2-valued Boolean function. But if you look at it carefully, you will discover that we are not getting solutions for X and Z together. We are trying to get a solution of Z in terms of X or of X in terms of Z. In this case, the problem will necessarily switch me to a big Boolean algebra. Because, for example, when I solve for Z in terms of X, the elements to which Z belong will belong to the Boolean algebra b to the power 2 to the k. Okay, next, please. The details here show us how, as I said, I end up with an equation g of z equal 1. And this function now is different from the original function gxz. It takes me from a domain b sub 2 to the power k capital to the power n to b to the power b of 2 to the power k capital, where this is the free Boolean algebra fb of x1, x2 up to xk. This means that the elements to which z belongs are the switching functions that can be constructed from the k variables, the kx variables. This new algebra will have capital K equal to 2 to the small k atoms and 2 to the power 2 to the power k elements. First, we can express gz by the min-term canonical form. This is just what we call min-term expansion in digital circuits. And if we can go next, please. Let me skip these steps because I will find difficulty explaining the mathematics. It's better to go to the example. So next, please. In this slide, I need to bring your attention to what we call the variable entered Cardinal map. This map has been developed in digital design to increase the variable handling capability of the map. In the 1980s, it was regular that it was known that the Cardinal map can be used for 6 variables at most. And but by having a variable entered map, which is a map inside which I do not just use the values 0 and 1, but I can use other variables, then maybe I can go up to 12 variables by having 6 entered and 6 map variables. But it was very important that we discovered later that this map, which was used just for B2, is actually the natural map for a big Boolean algebra. This discovery is very important because now all operations on a big Boolean algebra can be handled by map methods with a lot of convenience that I am going to show you through the example. If we can go next, please. Let us skip the mathematical derivations totally. I prefer to go to the example because then how much time is left for me? Next, please. Here there is, we introduce the variable n sub I, which shows, which indicates the number of appearances of an atom in the natural map of GZ. And then we discovered that the number of solutions for the Boolean equation that we had G of Z equal 1 is equal to the product of these variables n sub I. So clearly, if one of the atoms,
yes. Professor Ali, just I am interrupting you. I'm sorry to interrupt you. Could you please wrap up your talk within 5 minutes or so, because it is already 25 minutes. Just a request. If it is possible.
How many minutes are still left?
In fact, just 4 minutes are left.
Oh, so let me just jump to the example, please. If you can skip a few. If you just skip a few of the.
Thank you, Professor.
Go to the next slide.
Thank you, Professor.
Next, please. Next. We need to skip. There are many of them until we find a figure. If you can go next, please. Next. We need to go next until we come to a figure, because all of these. Oh, there are. I am sorry. I was very ambitious to prepare a lot of equations, and here in this slide there is just a mention of the don't care notation, which helped us to obtain the substantive solutions conveniently. But of course, I have prepared the paper in which all these mathematics and with references have been given in detail. If we go on next, please. Again, next. If you skip several, please skip all the text until we reach a figure. Oh, the discussion here was about the importance of use of map methods. I explained here why the use of maps was very convenient to supplement the algebraic methods. So next, please. Now we reach an illustrative example. There is equation 32 or equation 31 gives a function of x and y given in this form, in which we have two variables, x and y, but there is three what you call parameters or generators or whatever, c and a and b. They look like variables, but they are not variables. We need to express x and y in terms of a, b, and c. So if you go next, please. Here we expanded the function g of xy by the Boole-Shannon expansion. Next, please. This is an important figure. This is the natural map for g of x and y. As you see, we call this map a variable entered map because, as you see, what looks like variables a and b and c appear inside the cells, not just a and not just 0 and 1, and but these items which look like variables are not. They are just generators of the underlying Boolean algebra. This kind of representation helps us solve a lot of sophisticated problems, as you can see. Next, please. Here is the method to obtain a direct parametric solution by associating each atom by a certain tag. The tags for any atom are orthonormal. Next, please. And this explains how to obtain the other type of solutions. Here we can get do the elimination processes that we need for obtaining a substantive solution. Next, please. The figure here with the green loops shows you an important step. The elimination steps, which needs map folding, ends with a last step in which I can make use of the don't cares. And with the don't cares, I can get very good compact solutions. And these compact solutions are quite difficult to obtain algebraically if I just use algebra. Next, please. Okay, this will continue the solutions. Next, please. The final result of the solution is shown here, and we compare the two types of solution which turn out to be the same. An important item to mention here that the solution does not involve only non-uniqueness, but it will require a consistency condition. And that consistency condition will mean that the underlying Boolean algebra has collapsed to a smaller subalgebra. Next, please. Next, because these are just more details for the solution. Next, please. Next. In the past figure, instead of using just two parameters, which is the minimum number, I decided to use independent parameters for every atom. And this led to the solution. Note that these are the particular solution. Their number is 3,000 something. And still, I have managed to mention them because I get the solution for every atom separately. The solution for every atom is included here in a very compact space. Later, we developed this kind of solution into a solution obtained by what we call atomic decomposition of the function and the variables themselves. By the way, all the methods that we are using get us the same kind of solution. And now the situation has matured enough. You can go to the next, please. I hope it is the conclusions. Yes, next, please. We have made a revision, a quick revision. I hope I'll make the full paper which I sent to Professor Ram already. I'll make it available so that if you are interested, you are welcome to read it. And if in case you have any comments, you can contact me directly.